you. Hello, everyone. I'm from University of Southampton. As my postdoc, I'm working on resilience-based design of biologically inspired columns for next generation accelerated bridge construction. This project is funded by EPSRC. Dr. Kashani is the principal investigator, and this project also involves a number of academic partners and industry partners. Professor Fabrizio Escarpa from Bristol University, and Fiberline Composite and Jacobs. Any bridge structures during its lifetime can prone to extreme loadings, and bridge piers can play a key role in withstanding the lateral loadings and maintaining the integrity of the system. So, due to material aging and deterioration in bridge piers, their capacity can reduce, and if this reduced capacity combined with extreme loadings can result in severe damages in bridge piers. Conventional cast-in-place columns can fail at their base due to plastic hinges, which comes from maximum bending moment at the base. These conventional casting-place columns have some advantages. They've got higher energy dissipation, high damping, and very large plastic deformation. This very large plastic deformation can induce residual displacement in the whole structure. So after the severe loading, the whole structure, the whole bridge pier cannot come back to its initial stage, which means this system is not resilient. So as an alternative to cast-in-place columns, precast rocking columns are being used in accelerated bridge construction. For cast-in-place columns, bending mechanism is the main mode of failure, with tensile cracks at the concrete, compression, crushing of the concrete, or reinforcement yielding. In precast rocking columns, rocking of the segments and also self-centering effects of the post-tension tendon can withstand the loading. However, there are some shortcomings with precast rocking columns. High stress local damages can be observed at the compression surfaces, and also the system has a very low damping, as you can see in this plot. So, but this system is resilient and there are elastic deformations. So the desired behavior is to increase the damping and capacity of this system to have a behavior like the one shows on the right, and also to reduce the local damages at the contact surfaces. So what we are proposing here is a new column inspired from human spine. As in human spine, in vertebral discs between the vertebrae can help make the movement of the vertebrae more easier, and if the intervertebral disc damages, serious injuries can happen to the people. So, inspired from this, instead of likely we use some composite layers between the segments to act as intervertebral discs between the vertebrae. So this composite layer first must be designed so that they increase the damping of the system, and also because there's a flexible layer between the segments, local damages at the edge of the segments when the segment rocks can be reduced. As an option for using between the segments a composite layer, entangled composite wire materials are promising. As you can see, the strain or force deformation after the unloading, they comes back to the zero deformation, but they still have damping. The damping depends on the state of the wires relative to each other. If they are non-contact or they are slipping relative to each other, so they have lower damping than when they all stick together. So since I started this project 5 months ago, so I'm at the earlier stage of the project, and so far we have done the finite element modeling of this idea, which is very challenging. I used OpenSys software to model these structures. The segments were modeled by using beam column elements. As the segments are supposed to be rigid, so we used very large bending rigidity to have rigid segments. Also, for the post-tension gain cable, which connects the bottom to the top of the column, we used truss element. The most important part of our modeling, the most challenging part, is how to model the contact surfaces or the joints. So what we did, because when these two surfaces, when the two segments rocks, at the compression zones we have compression, but when the joints opens, at the opening there's zero tension. So what we used some springs to model the joints, and these springs are zero tension and they act only under the compression. So based on the previous investigations on the precast rocking columns, so these type of structures, the sliding is very small and negligible, so we used the horizontal restraint at the bottom. Also, we used a zero gap element between segments with a high horizontal stiffness to allow for the shear transfer between the segments. So we have these zero tension springs. If we use elastic zero tension material, which has been already implemented in the OpenSys, then we can have the precast rocking columns. So if we use the material that we are going to design for the composite layer to be used between the segments, then we have our biologically inspired column. So the model that we are going to, I implemented a model for entangled composite wire materials in OpenSys by programming in C++ and then linking to OpenSys to model the composite layer between the segments. So we did, before we start designing that composite layer by doing numerical simulation, we did a preliminary investigation on the conventional precast rocking columns. So we investigated the nonlinear statics and dynamics of the system. The important parameters are the aspect ratio, the height to width of the column, also number of segments, and also the initial post-tensioning force using in the tendon. So in the upcoming analysis, I assumed that the column's height is 3 meters, and then I changed the width of the column to reach different aspect ratios. For nonlinear static analysis, I did a pushover analysis. What I did, at the top of the column, we increased the force to, and then we monitored the displacement on the top and the shear force at the bottom to have the lateral force capacity of the system. So first, the effects of the aspect ratio. So as the columns becomes more slender, so we see that the base shear and also the moment at the base drops. Also, the pre-tension force at the tendon drops as well. Also, slenderizing the segment reduces the initial stiffness of the system as well. So as the number of the segments increases, so the moment capacity and the shear capacity of the system increases, but the tension force in the tendon remains unchanged. For the effect of the post-tensioning force, as it was expected, so increasing the post-tensioning force, it increases the base shear capacity of the system, also the moment rotation capacity. So also we did some nonlinear dynamic analysis. What we did, we used a sine sweep excitation with different frequencies and constant amplitude. We applied it to the structure, then we monitored the acceleration at the top of the column. Then we remove the transient part of the excitation and we extract the steady state response. For each frequency, we plotted its corresponding steady state response. As you can see, then we plot the acceleration response versus the excitation frequency. As it is seen in the below figures, then we did this, the same process for different base amplitude. At the very small amplitudes, because the joints are still closed, the system is linear, then we can see a resonant curve like linear systems. But when the dynamic amplitude increases, the joints starts opening, the system becomes nonlinear, basically geometry nonlinearity, and we see an instability in the solution around the resonance of the system. So we also monitored for a constant amplitude and constant frequency based excitations. We monitored the response, the vibration responses, also force responses at different across the joints over the height of the structures. And as you can see, the maximum responses occur at the base of the system, which means if we are going to improve the damping of the system, we need to find a way to damp the motion of the bottom segments. So if we are going to use a composite layer, the better way is to use it at the bottom segments to damp more rocking motion. So I also did some simulations using composite layer, what we call it our proposal inspired column, and without composite layer. Without composite layer, we did a cyclic analysis. As you can see, the loading and unloading for the red one, which is the without composite, they are the same, and there's no energy dissipation. But when we use the composite layer, so some initial findings which are promising, so potentially we see a high energy dissipation capacity. As the loading and unloading, there's a big area which shows the dissipation capacity of the system. Also, we see the zero deformation when the system comes back to its initial states, which is what we are looking for, which means resiliency for us. So, as I said, I have started this project 5 months ago. Then there is a lot to do in the future. So first, we need to use do some numerical analysis, both nonlinear static and nonlinear dynamic, using those composite layers. We need to optimize and design a composite layer. By design, I mean what initial stiffness or initial elastic modules we need. Also, the slope of the unloading. After we design the material, we need to discuss with our colleagues in Bristol University to manufacture these composite layers, and then we need to do large-scale experimental testing. After that, we need to calibrate our numerical model with the experimental data that we have. Then we can do a very comprehensive parametric analysis to propose a framework for designing of such bridge piers. To disseminate our results, we are organizing a workshop on accelerated bridge construction, which will be held in University of Southampton, June 2020. More information will be found at this website, and this website will be updated very soon. Also, we are trying to organize a special, we haven't organized it yet, but we are trying to organize a special issue on accelerated bridge construction in Journal of Structural Engineering for 2020. At the end, I highly appreciate the help and support received from all the institutions involved in this project, EPSRC, University of Southampton, University of Bristol, Jacobs, and fiber line composite. Thank you for your attention.